Today we're going to be talking about stress and strain calculations. So, stress is going to be symbolized by the Greek letter sigma, which is this O with a little line over it, and is force over area. Strain, what happens is when you apply a stress, like pulling something apart, we call that tensile stress, or we can push it together and we call that compressive stress. And its units are either like pounds per square inch or newtons per meter squared. So let's look at this example. We have a statue here that weighs 2,248 pounds and rests on a horizontal surface at the top of a 3-meter tall vertical pillar. That's this pillar. The pillar's diameter is 1.65 feet and is made of granite with a weight of 3,525 pounds. Find the compressive stress at the cross-sectional located at the base of the smaller pillar. So we're looking just up here. So the stress is force over area. So we have to figure out what is the force. Well, it's going to be the weight of the statue plus this pillar. So we have to add those two together. 2,248 pounds plus the 3,525 pounds. That gives me 5,773 pounds. The area is then going to be, because it's a circle, cross-sectional area, we're going to use this, the diameter. So we're going to use the area of a circle, so pi r squared. So pi r, the radius, which is just half of 1.65, and that gives us our area. So we put that into our calculations. Force of 5,773 divided by the area of 2.14, and that comes out with a stress of 2,697.6. And that's pounds per square foot. All right, now strain, on the other hand, is the Greek letter epsilon, which is the E-looking one. And it is how much longer something gets compared to its based on its original length when it pulled on. So the Golden Gate Bridge has a 2.7-inch diameter vertical cables, these guys right here. The longest of these cables is 500 feet long and has a strain of 8.33 times 10 to the negative fifth. What is the change in length of these cables? So we can look at it, and we're looking for its change in what is the change in length. So this delta L. So we move our L over and put it over. So we get our strain times our original length. So 8.33 times 10 to the negative fifth times 500, and that comes out as 0.041 feet. Or if I change that into inches, that is a half an inch. So it is lengthened by just a half an inch. Now we can put this into a stress strain curve, and any material can actually put into a stress strain curve where we pull on it and see what happens to the material as the stress goes up, and then what happens to the strain as you increase the strain, what happens to the stress. So concrete is not is lower than cast iron, and mild steel much stronger. So grab a paper clip while you're at it, and just pause the video and just grab a paper clip. Did you grab a paper clip yet? Grab a paper clip. All right, so when you bend it, that paper clip, it's going to bend ever so slightly. Don't bend it yet, but what we're going to do is if you take a piece of spaghetti and bend it, it's going to break and brittle materials will just shatter. But the paper clip doesn't do that. It does this. It's going to bend, but then it's going to do this little thing. We're going to look at this. Now, point 1 is called the ultimate stress, right here at the top of the point. Point 2 is the yield strength. 3 is the rupture area. And 4 is the strain hardening region. And 5 is the necking region. Necking, when I say necking, that means the material gets thinner as you pull it apart. So as you pull these materials, they get thinner and thinner. So what I want you to do is pause this video, and I want you to draw this diagram. All right, so now you have this elastic region. This region here is what we call the elastic. Now take your paper clip and bend it, but don't bend it too far that stops, it deforms. It's just ever so slightly so it snaps back into its original shape. This is referred to as the elastic region, when materials will snap back to its original shape. Then you have the yielding. This is when it will deform and change its shape. When you bend that paper clip so far, it starts to actually bend. Now, as you wiggle that paper clip, you can start wiggling it back and forth, back and forth, back and forth. If you do that, you'll start to feel that it gets harder and harder to actually bend. And you are actually you're getting up to here where it's called strain hardening. You're actually making the material harder. You'll get to a point where it's actually the strongest that material will ever be. And eventually, if you continue wiggling it back and forth, that material starts to deform so much, it starts to neck. You can't really see it on a paper clip unless you had a microscope, but you could actually bend it and you would actually see it starting to neck down, and to the point of then eventually it would fracture and snap the paper clip in sections. So a true stress and true strain will happen like this, where it will bend, it will yield, and then it will rupture. And this is what that necking idea happens, and then finally rupturing. So here it is. If we look here, we have our diagram, and again, we're going to label these, and you can actually label them on your thing. We're going to have points 1, 2, 3, and 4, and 5, and we'll talk about this. So the first region is this region, the yield strength. When we have this region here, this is the elastic region. And this elastic region is actually linear, and it is a ratio of the stress and strain. And the ratio between the stress and strain is the Young's modulus. That is the same one that we dealt with earlier. Now, as you get past this point 2 here, we get us what is called the plastic region. And this is when the material starts to break. So the elastic region is points 1 and 2, where the material will return to its original shape, and it's linear, and that linearization actually gives us what the Young's modulus looks like. So this is the Young's modulus. This is just a rearrangement of it. The yield strength at point 2 is when the permanent deformation occurs. It starts to bend and won't go back to its original shape. So that's here. Now, after that, you got what is called strain hardening. The material will be loaded again at point 4, and it will continue up that little hill until it reaches the top of that hill, and this is when the material starts to get stronger. You can actually make materials stronger by what we call strain hardening, or you start hitting it and start destroying that crystalline structure, and it makes it harder. At the very top, you hit the largest value of that stress on the diagram, and we call this the ultimate tensile stress. This is the maximum stress a material can support without breaking. Then it starts to neck down at point 5, and eventually goes down to the fracture, where it will snap, and it starts to neck down, and then eventually snaps and failure occurs. So here is an actual stress strain curve for A36 steel, mild steel. So as you can see, it goes up. Now that slope right there would give us our Young's modulus. It's a fairly steep slope. Remember how our Young's modulus was a fairly large number. Then it starts to deform and starts to become plastic, and then it has this. This is our strain hardening. Eventually gets to its ultimate hardness, necks down, and then failure. So what I want you to do is when you're done with this video, go to Canvas and open up this PowerPoint, the same PowerPoint, and you can watch this video, and the video will actually show you this processing. You can actually see it for real. This would make this video way too long if I showed you it here, but it's a really nifty video. Now, the characteristics of materials are described as this: strength, hardness, ductility, brittleness, and toughness. Strength is just how much is a measured property. You can actually give something how strong it is, or by quantifiably telling it how much stress over its tensile strength. Hard carbon steel and metal alloys are higher than their pure metal iron. Ceramics also exhibit high strength characteristics. Hardness, on the other hand, is when you take something and indent it or wear it. So what they do is they take like a diamond-tipped needle and hit it and see how far that indented with the same amount of force. That is called the Rockwell test, and the Brinell is very, very similar to that. It just sees how far can you indent something under a certain load. Hardness and strength usually correlate but do not necessarily relate. Something can be hard, usually is stronger, but it's not necessarily all the way because it deals with the intermolecular bonding. High-strength materials are typically resistant to wear and abrasion. So here are some of the materials. You can see diamond at 8,000 is the hardest material known to man, but you can have stuff like titanium carbide or tungsten carbide, which is used in cutting stuff like steel. You got tool steel, which cuts regular steel, and they're much harder than regular stainless steel or mild steel. But these are harder than copper and aluminum. So aluminum being the softest, I can cut something with any of these harder stuff. Sand is actually harder than even tool steel, so I can cut things. So sometimes you think that sand is not that hard. Actually, it's one of the harder materials. Now, ductibility is the ability for properties to deform before failure. A ductile material can be pulled or drawn into pipes or wires and other structural shapes. Materials like low carbon steel, aluminum, copper, and brass are very, very good ductiles. Brittleness is the measurement of how the inability to deform before failure. Something that goes up really high and then fails and doesn't have that doesn't last long is what we call brittle. Something that can deform and has a longer strain is called ductile. So things, example of ductile materials is glass, carbon, high carbon steel, and ceramics. Now, material properties. Toughness is the measurement of the material's ability to absorb energy. It's measured by two methods. It's a calculus term called integration of the stress strain curve, which we won't deal with, or it's called the Sharpie test, where you hit a material with a hammer and see how much energy was taken out on impact. And so here's an example of this. This is the Sharpie test, and you have your piece here with a little notch in it, and then you have this big giant swinging arm, and it comes down and literally will whack that piece of metal, snap it in half, and then that swings up, and they measure how far it went up, and then based on how far it went up, they can actually figure out how much energy it took to break that material. So that's the Sharpie test. It takes potential energy, turns it into kinetic energy, and then does work on the material, and that work then is taken out, and then the hammer continues flying off, and it gets reabsorbed back up to potential energy, and you just see how much energy was lost to it. So here's an example of a Sharpie test for some high carbon steel versus low carbon steel, stainless steel, and stainless steel different temperatures maintains its strength, but high carbon steel really it takes out a lot of energy, and as the hotter you get, the more energy it absorbs out. Now, fatigue happens when you repeated application of stress over a long period of time, oscillating loads and vibrations. So the maximum stress decreases as the number of loading cycles occurs. So as you continue cycling, steel gets really. Now, some materials will continue going until they reach no endurance limits. Aluminum can continue having these cycles on it forever, and it will never fail, but steel will. Now, factors affecting materials property is temperature. So increasing temperature will usually decrease the modulus of elasticity, decrease yield strength, ultimate tensile strength, hardness, and increase ductility, decreasing the brittleness. Also, environments such as sulfurs, chlorines, oxygens, and water, radiation, and pressure can also affect material properties. So the ways that they alter materials is by alloying it, with adding materials such as carbon, chromium, molybdenum, nickel, tungsten, magnesium, aluminum, copper, magnesium, silicon, zinc, or aluminum or magnesiums within aluminum. You can also heat treat them by annealing and hardening, and these can also cause strengthening. You can temper it, hot working it, cold working it. These can alter the material's property, creating more and more particular interesting shapes. And then corrosion control is being the ability to stop corrosion due to oxidation and other chemical reactions by painting it or adding chemicals that will actually prevent the chemical reaction from happening. All right, this was a long enough video, and I'll let you guys have any questions, write them down, and then ask me when you get into class.